right, share my screen again. Okay, so chapter 5, if you haven't dug into it yet, there's actually a lot in the chapter that we're not really covering. So where I encourage you to really dig in and read the chapters for 3 and 4, for chapter 5, I would actually take a different approach on that one. I would look over, don't try and work the homework problems first, but look over the homework problems first, and then go into the chapter and really drill into the parts that look like they belong to the homework. Because there's a ton of stuff about interest rate theory and a lot of other things that we've decided is kind of beyond the scope of this class. All we're really going to look at in chapter 5 is the 3 types of cash flows we dealt with in 3 and 4, lump sums, annuities, and perpetuities. And we're going to add a little extra wrinkle, and that is what happens when you have more than one compounding period per year. Because most of the cash flows we're going to run into in our lives, most of them are going to have monthly payments, right? Your cell phone bill, your car note, your mortgage, all that stuff requires monthly payments. And so what we have happening there is you actually have compound interest accruing within the year. Every time you make a payment, it's got a little bit of principal and a little bit of interest in it. That interest accrues interest, and so we've got compounding happening inside of the year. So when we're working problems with those kind of payments, we've got to deal with that. All right. And so the thing we need to know is that in the US, any interest rate on anything that we're borrowing is reported as an annual percentage rate, or APR. All right, so anytime you look at your credit card statement, your car note, the contract for your car note or your mortgage, you'll see APR equals. APR stands for annual percentage rate. And now APR has a specific definition. It's defined as R times M, where R stands for the effective interest rate per period. So if it's monthly payments, that means the monthly effective interest rate. And M as in Mike, stands for the number of compounding periods per year. So if we have a loan that requires monthly payments, then there are 12 compounding periods per year. Okay, let's look at a homework problem to play with this and make it a little bit more concrete. Okay, so I've pulled up the example for number 11 from chapter 5. And number 11 says you're looking to buy a car and you've been offered a loan with an APR of 6.3% compounded monthly. And we've got 2 questions to answer. A, what is the true monthly rate of interest? And B, what is the EAR, or effective annual rate? Okay, let's take these one by one. Ooh, that's supposed to be an A. It's just a little diamond. There we go. Okay, what is the true monthly rate of interest? In order to find this, we're going to take advantage of the definition of APR, where APR is equal to R times M. Right. The APR we know in this case, and now that we're using the calculator, I'll say this several times. Anytime we're doing math with an interest rate, we've got to convert it to a decimal. Anytime we're putting an interest rate into the time value of money keys on the calculator, we want it in percentage format. So it can kind of be confusing to bounce back and forth between those two at first. But that's the way to keep track of it. If you're doing arithmetic with it, it's got to be a decimal. If you're putting in the time value keys, it's got to be in percentage format. Here we're going to do math with it. Or arithmetic with it. So we're going to record the APR of 6.3% as a decimal. So that's 0.063 is equal to R. R we don't know. That's our monthly effective rate. M is the number of compounding periods per year. Since this loan requires monthly payments or has monthly compounding, we've got 12 compounding periods per year. All right, now we just want to solve for R. So I'm going to divide both sides by 12. All right, and those 12 divided by 12 is 1 on the right-hand side, so I'm just left with R. So I've got 0, thought it was a triangle, 0.063 divided by 12 is equal to R. All right, and 0.063 divided by 12 is 0.0053. which I can't do in my head, but we did it yesterday in class, so I just happen to remember what that one stands for. Or if we write that as a percentage, it's 0.53%. Okay, and that is per month. And that is the answer to part A. That is the true monthly rate of interest. All right. So when banks are looking to set interest rate on loans, they typically won't, internally, they're not worried about APR. APR is just what they have to report externally, because they're typically looking at loans with monthly payments. What they look at is the monthly effective rate. They set that, and then they just multiply it by 12 to get the APR. All right. So in terms of your true borrowing cost, the APR doesn't quite capture it, and we'll see that in part B. The monthly effective interest rate is your true borrowing cost. Before we go to part B, are there any questions on how to get that number? And I'm just going to take a peek at the chat window, which means y'all are going to be looking at yourselves for a second. All right. No? All right, well, let's go on to part B. Part B says, what is the EAR, or effective annual rate? The issue with the annual percentage rate is that it ignores the effects of compounding, right? Meaning, as we saw when we were calculating future value, when you have multiple payments, then each payment has a little bit of interest in it, and that interest is going to earn more interest. And so you've got this compounding effect of interest on interest happening, and the APR ignores this effect. They just take the periodic effective rate times 12 and good enough, right? So if you've got more than one compounding period per year, the APR is actually underreporting the effective rate. Okay. So in order to capture the effects of compounding, and also if we want to compare different annual percentage rates, we need to convert them to the same effective periodic rate. That can be monthly, it could be weekly, it could be anything, but typically we'll convert it to an EAR, or effective annual rate, in order to look at the true borrowing cost or to compare the rates on different loans. So let's look at part B. This is where we want to convert it to an EAR, and we have a formula for that, where EAR, or the effective annual rate, is equal to 1 plus the APR, whoops, let's use the generic formula first, APR divided by M raised to the M, and then minus 1. So this should actually look pretty familiar. This chunk right here, the 1 plus APR over M raised to the M, that looks an awful lot like the future value, time value of money equation, right? Where the future value is equal to the present value times 1 plus R raised to the N. That's exactly what's happening here. We're capturing the effects of compounding. In this APR over M right here, remember the definition of APR? I'm just going to do this off to the side. It's not related to this problem, or not related to this specific formula. APR equals R times M. Well, if we solve for R, that's going to be equal to APR over M. All right, well, that's exactly what's going on in this formula right here. APR divided by M, in this case, for this problem, is our monthly effective rate. So we're taking 1 plus the monthly effective rate, raising it to the number of compounding periods per year, to capture the effects of compounding. All right, and it's on your formula sheet. I meant to show the other one because I want to talk about it. In the Chapter 5 formulas, you've got the effective annual rate formula right here, and you can bounce back and forth between the EAR if you're given the APR, and you can also find the APR if you're given the EAR, right? And these two formulas, EAR and APR, are actually the same. One is just solved for effective annual rate, and the other one is solved for annual percentage rate. One thing I wanted to point out though, the formulas here, you can see little r as APR over N. N is in November, and I've been writing M as in Mike in your notes. And that's not a mistake on my part. These formulas on your formula sheet are copied from the text. They use N throughout the text, and I think that's unnecessarily confusing. The reason for that is because N is used in the time value money formulas to mean the total number of compounding periods, right? Or the total number of payments. And that previous problem that we looked at, the bond was outstanding for 16 years. So our N was 16. There were 16 total compounding periods. The thing that's in these formulas, EAR and APR, is not the total number of compounding periods. It's the number of compounding periods per year. All right, so if we've got monthly payments, this N is 12. If this were, say, a 4-year loan, then the N, the total number of compounding periods, would be 4 times 12, or 48. And I know that's you're probably going, what the heck is he talking about? We'll work a couple of problems and see this at work. All right, but that's why in my notes I'm recording this as M as in Mike, and on the formula sheet it's N, and I don't like that they use N for those. Okay, so let's plug in. We're still working the same homework problem where the APR is 6.3% with monthly compounding. So let's plug that into our EAR formula. So our APR is 6.3%, expressed as a decimal is 0.063. M, our number of compounding periods per year is 12. So we're going to divide that by 12, raise it to the 12, and then subtract 1 off of it. So that's going to be EAR is equal to 1 plus. We already did 0.063 divided by 12 above. We know that that's 0.0053 raised to the 12 minus 1. So that's EAR equals 1.0053 raised to the 12 minus 1. All right, and I think I remember that, but let's type it in just in case. All right, 0.0649. Or if we're going to write that in percentage format, that's 6.49%, and that is per year. Hi, so interesting. In part A, we found the effective monthly rate, the true borrowing cost, expressed in months. It was 0.53%. Expressed as an annual rate, the true borrowing cost, the effective borrowing cost, is 6.49%. Now notice that that's a good bit higher than the 6.3% APR that we were quoted on the loan, and that's because of those compounding effects. Every single month there's interest on interest accruing, and so when that compounds 12 times within the year, it bumps the effective borrowing cost up to 6.49% on us. Okay, any questions on part B? All right, I'm going to stop sharing for just a second so I can see the chat. No, no questions. All right, I've either put you all to sleep or you are crushing it. Probably a little of both, huh? There's 70 of us on this call. All right, onward then. There's one hint I want to throw out there because you're going to use it in the chapter 5 homework. And that hint is this. You'll be asked to either directly calculate the balance of a loan at a particular time. So say you took out a mortgage 5 years ago, you've been paying on it for 5 years, and you need to know how much principal is still outstanding. That is how much you still owe on the loan after you've made a set number of payments. Or it may be an intermediate step on one of the problems. Like in order to get to the final answer, you'll have to calculate the outstanding balance on a loan. And the way that you do that, or one way that you can do that, is that the balance on a loan at any time is the present value of the remaining payments. Right? So if you've made payments for 5 years, it's a monthly mortgage, you've made 60 payments on it. If it was a 30-year mortgage, you would have paid 360, you would have paid for 360 months, you made 60 of them. So you would find the present value of the 300 remaining payments, right? The present value of the payments that you have yet to make. Okay, and I know for sure that you'll use this trick on number 17 and 18 in the chapter 5 homework. So I just wanted to arm you with that going forward. We're not actually going to do those together. I want you guys to kind of work through those and then we can talk about them next week if you get stuck on them or want to know more about them. But I just wanted to give you that heads up on those homework problems. So the balance on a loan at any time is the present value of the remaining payments. All right, let's check out another homework problem. This one's also from chapter 5. It's number 16. Number 16 says you have just taken out a $31,000 car loan with a 9% APR compounded monthly. This loan is for 5 years. When you make your first payment in 1 month, how much of the payment will go toward principal and how much will go toward interest? All right, and there's a note there. Be careful not to round to any intermediate steps to less than 6 decimal places. We're going to use stored values, so that won't be an issue for us. Okay, I picked this problem out on purpose because the previous problem we looked at had us looking at the monthly effective rate inside of the APR. This problem is going to demonstrate how that is used, how it's at work inside of a car loan. So this is a time value money problem. So we're going to follow that 3-step process. We're going to start by mapping the cash flows. Oops. I wish y'all could see what I'm doing at my desk. It's pretty funny. I'm using an electronic drawing tablet, and I have an actual ruler that I'm using to make a straight edge. It's a hilarious mix of old and new technology. Okay, so we've taken out a $31,000 car loan. I'm going to look at this loan from my perspective as the borrower. That means at time period 0, the bank gave me $31,000. So I had a $31,000 cash inflow. I, of course, didn't keep that money. I turned around and gave it to the car dealership. And I promised to make monthly payments on this loan at a 9% interest rate, but that 9% is an APR. So I'm going to make sure I label it as an APR in my timeline so that I don't forget that. So the bank gives me $31,000 today. 1 month from today, I'm going to make some payment on this loan, and I don't know what that is. So I'm just going to say minus PMT on my timeline to stand for payment. I know I'm going to have some cash outflow 1 month from today. I just don't know what it is yet. 2 months from today, I'll have that same cash outflow, and that will continue for some number of months. So the loan is for 5 years. I'm making monthly payments. How many total payments will I make on this loan? That's a question to y'all.
Is it 60?
Yeah, 60. How did you get that?
5 times 12.
Yeah, so it's going to be 60 total payments. And the way we get that is the loan is for 5 years. We're paying on it for 5 years, but we're making 12 payments per year. So we're going to make 60 total payments on this loan. One per month. Okay, do we have everything on here? We know the present value of this loan, and we know the cash flow at time period 0. We know we've got monthly payments, we just don't know what they are. We know the total number of payments, and we know the interest rate. Okay, so we've got level cash flows. The same payment is going to be made every single month. The same cash flow at regular intervals. The first one is at the end of the first month, and then they stop at some point. What does that tell us? What sort of cash flow are we looking at here? Lump sum, annuity, perpetuity? Y'all tell me.
It's an annuity.
Yeah, it's an annuity, and with the payments at the end of each period, more specifically, it is an ordinary annuity. Oh goodness, why does it think that looked like a oval? All right, because the payments are at the end of each period, we know it's an ordinary annuity. Once we identify it as an ordinary annuity, there are two more things that we know. The first one is we can use the formula to find payment. Specifically, we can use the present value of an ordinary annuity formula. And the reason we would use the present value of an ordinary annuity is because we're given the present value. If I click over to the formula sheet here for just a second, go up to the chapter 4 formulas. I've got the present value of an ordinary annuity right here. Since I know what the present value is, I can plug that in. I don't know the cash flow. That's my unknown, but I do know the interest rate. I do know the number of compounding periods. So I'd plug in all of the information, and I've got to solve this thing for C. I've got to find the payment, which is totally doable. And if we have time and someone is interested, we'll look at that together. But more interesting to us at the moment, the second thing that we know is that we can also use the time value money keys on the calculator to save us some legwork. So let's go straight for those. Okay, N. This is where that N versus M thing starts to come into play. N is my total number of compounding periods. If we're talking about an annuity, that's the total number of payments. On this loan, that's 60 total payments. All right, so I'm going to make 60 payments of whatever I'm going to make. Now, that is 60. I'm going to put the units on here because it matters. That is 60 months. When I go to put in my interest rate, that's I over Y, or interest rate per year, the units on the interest rate that I put in have to match the units on N. So we've got 60 months here. That means I need to plug in the monthly effective rate on I over Y, right? And we've already seen how to do that on the previous problem, where the periodic effective rate, I'm just going to write it out to the side here, the periodic effective rate, or R, is equal to the APR over M, where M is the number of compounding periods per year. So R in this problem is our 9% APR divided by 12. All right, so over on I over Y, I'm going to actually write in 9 divided by 12 equals, and I think I remember it, but just in case, let's type it in. 9 divided by 12 equals, yep, 0.75. Okay, that's 0.75. And that is per month. All right, so starting in chapter 5, we're going to have to really pay attention to the frequency of the payments. And another way of saying the frequency of the payments to say the number of compounding periods per year. We need to make sure that the units on N and I over Y always match. So if we've got the number of months on N, we need the monthly effective rate on I over Y. If we've got annual payments like we had all through Chapter 3 and Chapter 4, then N is the number of years, and we want the annual effective rate on I over Y. Now, if there's only one compounding period per year, this APR formula, this effective periodic rate, is the APR divided by M. Well, if M's only 1, then the APR and R are exactly the same. There's no difference between the two. It's just if we have more than one compounding period per year that we have to worry about it. Okay, before I keep going on this one, any questions about why we're doing 9 divided by 12 for I over Y? Or where any of those numbers are coming from? Okay, let's plug in the rest of our variables here. Present value, that's what happens at time period 0. In this case, we actually know the present value of the annuity. It's $31,000 because that's what the bank gave us, and we're going to pay it back over 60 months. I've adopted the perspective of the borrower, so that's going to be a cash inflow or a positive $31,000. Payment is what I'm solving for, so I'm going to put a question mark there. And future value is the weird one. I'm going to put a 0 here. Now, that is not because the future value of this annuity is 0. It has a future value and it's not 0. Okay? Because we're solving for payment, we're solving for one of the cash flows. That means on the other two cash flow keys, what we're actually putting on them is what cash flows happen at that point on the timeline. So for example, we're solving for payment on this problem. That means on PV, we're actually going to put the cash flow that happens at time period 0. That's cash inflow of 31,000. And on future value, we're going to put the cash flow that happens at the end of our timeline in addition to the payment that we've already entered. When we said N is 60 and we're going to solve for a payment, the calculator already knows that there's a payment, a 60th payment at the end of the timeline. We would only put something on the future value key if there was another cash flow in addition to that last payment. In this case, there is not. When we make the last payment on the loan, it's paid off and we're done. So that is it for this one. All right, let's put these guys in the calculator. I'm going to start by clearing out my time value money keys because the last problem I worked is still in there. So I'm going to hit second clear TVM to clear it out. And that makes everything 0. And then I'm going to work left to right key by key again. I'm going to start with N. So I'm going to type 60 and press N. Now for I over Y, this is important. We want to minimize rounding errors. If we look back at this formula, this R here is the same thing as I over Y. That is raised to the N. In this problem, N is 60. So if we make a rounding error when we're putting R into our calculator, it is going to get compounded 60 times exponentially. All right, that's going to create a huge rounding error. So we want the number that's going on the I over Y key to be as precise as possible. So when I need to enter something into the I over Y key and it's 9 divided by 12, I'm actually going to go ahead and put that into the calculator. I'm going to type it in as 9 divided by 12 and then press the equal sign to get it to do the division. And while my calculator is set to show me 4 decimal places, it works that out internally to something like 12 or 13 decimal places. Of that number on the I over Y key for me, not just the 4 decimal version that it's showing. Now, in this one, 0.75 comes out even, so it doesn't matter. You could just type in 0.75, but a lot of them will not come out even. It'll be this ugly irrational or repeating decimal that you want to get the full number of decimal places. Alright, so we've got over Y. Jessica, I see your question. Let me walk through this and I'll come back and address it again. All right, present value is 31,000. So I'm going to type in 31,000 and press present value to store it. Future value is 0, so I'm going to type in 0 for future value. I skipped over payment because that's what we're solving for, and now I can hit compute payment. All right, and it's going to give me a negative. That's because I adopted the perspective of the borrower. I received $31,000, and that means the monthly payment is going to be a cash outflow for me. So it's going to be an outflow of $643 and roughly 51 cents. So minus 643.51. Okay, so that's the amount of my monthly payment. I'm not quite there yet. That was a step on the way to solving this problem because what it asked for is how much of that payment is interest and how much is principal when we make our first payment. But before we go to the next step, does anyone have any questions about how we're getting that number? If you're typing it in, are you getting that number to come out okay, or what else is going on? Okay, so we had a question about, it says, can you explain the yearly rate for I over Y again? And I think I know what that's asking, but if I'm not going to hit it here, just feel free to say, no, that's not quite right. I still don't get it. So on the I over Y key, this needs to be the effective rate that matches the periods that are on the N key. So if we're putting in the number of months for N, then we need to put in the effective monthly rate on the I over Y key. If we're putting in the number of years for N, then we need to put the annual effective rate on I over Y. And now we don't get to just pick which one we do. It's going to be driven by the cash flows. In this problem, we've got monthly cash flows, so we have to do everything in months because the interest is compounding monthly. We can't just decide we're going to convert everything to years. The only time we put in the annual effective rate for I over Y is if we actually have annual compounding periods where payments are happening once per year. Or like the bond, we just had one payment at the beginning, one payment at the end, and they wanted to know the effective annual rate of interest. So everything was in years in that case. Does that clear it up at all, or was the question about something a little bit different? Okay. All right, so as we said, we're not quite there yet. We know on this loan we're going to make a monthly payment of $643.51. What we still need to figure out is when we go to make our first payment at the end of the first month, how much of that payment is interest and how much is principal. Where the principal amount of the payment is what's actually going towards paying off the loan. It's reducing the amount that we owe. The interest on the payment is just rent on the money. It's just a fee that not a fee, it's the interest the bank collects that compensates them for loaning us the money up front. It doesn't actually go towards paying our loan down. All right, so here's how we get that. I'll leave that up there so we can see it. All right, so the amount of interest. The way we find that is by taking the loan balance and multiplying it by the periodic effective interest rate. All right, now our loan balance is going to change with each payment. Every payment we make is going to reduce the balance. But on this problem, it was asking for the first payment. When you make your first payment in 1 month, how much will go towards principal and how much will go towards interest? So we haven't made any payments yet. That means our loan balance, when we go to make this first payment, is still $31,000. All right. To figure out how much interest we owe for that month, the bank is going to take that loan balance of 31,000 and they're going to multiply it by the periodic effective rate, which is the annual percentage rate divided by the number of compounding periods. And we're doing math with this rate here. So instead of it being 9 divided by 12, we're going to do 0.09 divided by 12. All right, and we already know that that's 0.075. All right, so let's type it in just so we can store the number. 0.09 divided by 12 equals 0.075 times 31,000 is $232.50. All right, so the amount of interest that we pay when we make that first payment is $232.50. That means that when we write that check, we give that check of $643.51 to the bank, $232.50 of it is just interest. It's just the money that the bank is collecting to compensate them for lending us the 31,000. It doesn't reduce the amount that we owe at all. Right? The next step, once we know that, to figure out the amount of principal is to take our monthly payment that's fixed, it's the same every month, and subtract out the amount of interest. Right, so our monthly payment was $643.51, right? Yeah, 51. All right, that's the total check that we wrote to the bank, but we need to subtract out $232.50 because that went just towards paying off interest. Okay, so let me say this plus. All right, so that turns out to be $411 and a penny, roughly. Right, so of the $643.51 that we paid the bank, only $411 and a penny of it went towards reducing our loan balance. Okay, so those are the two answers for this question. I want to take it a step further so we can see how it works, but do y'all have any questions about what we're doing here or how to get those numbers? No worries, Jessica. Okay, let's take this one step further just so we can see how it works. And I've only got one other problem I want to go through, and we got 15 minutes, so we are good to go on time. Okay, this next step is not part of the problem. It's just to kind of see how this process plays out over time. So let's say we wanted to look at the second month's payment. So the next payment that we make, how much of that payment goes towards principal and how much goes towards interest. All right, well, we'd go through the same process, but the amount of interest is going to change on the second payment because it's the loan balance times the periodic effective rate. Well, our loan balance changed. It was $31,000, but we repaid $411.01 of that. All right, so when we look at the second payment, we calculate the loan balance in the second month, and it's no longer 31,000, it's $30,588.99. And we multiply that times the monthly effective rate. And the amount of interest that we owe is a little bit less. All right, so on the second payment, we pay back 229.42, or we pay 229.42 times interest towards the interest. And notice before it was $232.50. So we're paying a little bit less in interest. Now what that means is we're paying back a little bit more in principal. When we take that monthly payment that's still fixed, $643.51, we subtract out the interest that we're paying. Okay, and on that second payment, we're paying back $414.09 worth of principal. So it was $411, now it's $414.09. Not a big difference, but that trend continues and it also accelerates. Every month, the loan balance is going down, so we owe a little bit less interest. So a little bit less of each month's payment is going towards interest, and a little bit more is going towards principal. Right? And that trend will kind of accelerate. More and more of the payment will go towards principal until finally the last payment on the loan is almost all principal because you only owe a couple $100 on the loan at that point. So you only owe a tiny little bit of interest. And the monthly payment on this loan is calculated such that so that very last payment will have just enough principal and just enough interest in it in order to fully pay back the loan. We call it amortization. That's a self-amortizing loan. Yeah, it wasn't really part of the problem. You didn't have to do that to answer the question. I just thought it would be interesting to see how that worked. Any questions or anything you want to know about how amortization works? Okay, let's look at one last homework problem, then I think you'll be in pretty good shape to tackle the Chapter 5 homework. Um, in in addition to looking at cash flows where there's more than one compounding period per year, there's another section of Chapter 5 that we care about, and that's the fact that stated interest rates, whether it's an APR or even an annual effective rate, don't tell us the whole story. And that's because we don't necessarily care about what our rate of return is or what the borrowing cost is. What we really care about is the change in purchasing power. That is, what can we buy with the money, right? Because the money itself is worthless. For the most part, we can't even use the dollar bills. Like the physical thing right now is is almost worthless. It's all electronic at this point. So what matters to us is what we can buy with it. And for example, what I mean by that is, let's suppose that over the last year, you've been investing in the market and things have been going great. You earned a 15% rate of return on your investments. That sounds awesome. But now suppose over the same year that inflation was 20%. That is, average price levels in the economy rose 20%. Now you earned 15% on your investments. So what actually happened is, from last year to now, you can buy 5% less stuff than you could at the beginning of the year. All right, so your purchasing power actually eroded. Although you had a positive, wonderful sounding 15% rate of return, you're actually worse off in terms of what you can buy. So we need a way to take care of that, or a way to account for it. And what we look at is what we call the real rate of interest. And it captures this change in purchasing power. And the formula is this guy right here. The real rate is equal to the nominal rate, where the nominal rate is that stated rate. It's the APR, EAR, whatever we're working with, minus the inflation rate over 1 plus the inflation rate. And that's on your Chapter 5 formulas. All right, got that right at the bottom of the page there. And I just copied and pasted that into our notes. Right, so this is what we'll use anytime a problem is asking us for the real rate, or it's giving us information on inflation. This is the guy we're going to use. And this is an adaptation of the Fisher equation, PHI Fisher. That's not true, FI Fisher, for the economists that came up with this idea, if you want to look up more on Fisher. Okay, so the homework problem that uses this, or one of them anyway, is number 19. Number 19 says that in 1975, interest rates were 7.85% and the rate of inflation was 12.3% in the United States. What was the real interest rate in 1975? Another way of asking the same question is, how would the purchasing power of your savings have changed over the year? Another note there, not to round, but that's okay, because we'll use stored values and it won't matter. All right, it's flat out asking us for the real interest rate. We see information on inflation and interest rates, so we know we're going to use that adaptation of the Fisher equation, where the real rate is equal to the nominal rate minus inflation divided by 1 plus inflation. All right, the nominal rate are just the stated interest rates, and we're doing arithmetic with these, so we're going to do them. We're going to use them as decimals. So 0.0785 is the nominal rate. Uh-oh, I broke something. OneNote restarted. There we go. Okay, the nominal rate is 7.85% expressed as a decimal. That's 0.0785. Minus the rate of inflation, it says 12.3%, so expressed as a decimal is 0.123. All divided by 1 plus the inflation rate, so that's 1.123. All right, so let's type that in. I don't remember the answer to that one. 0.0785 minus 0.123 equals divided by 1.123. All right, so a negative 0.039, what was that? 6. Or negative 3.96%. All right, so our real rate of interest was negative 3.96%. That means our purchasing power declined, it decreased by 3.96%. That means we could buy about 4% less stuff at the end of the year compared to the beginning of the year. All right, any questions on that one?